So you can forget the contribution from this surface and that surface, right? So only the curved surface. So what you'd have is going to be the integral of S dot dA for the curved surface, and that would give you, so mu naught cancels, which is a good thing, IV over 2 pi A squared L S minus S hat integral dotted. So what should I write for dA? And remember, this is now here, S should be what? A, because we are evaluating over a closed surface which encloses this cylinder. So we have to evaluate it at S equals to A. Dotted with dA, so dA, how can I write it? So basically, even you don't have to carry that integration because it's a constant over the entire surface, so I can just simply multiply by, if I forget the integral, this is basically you multiply by 1. 2 pi A times the length L. And the unit vector to that area is what? S hat.
Where's the second icon?
It was supposed to be
This is supposed to be.
You said S
said
when
S
you wrote
when you
it, so that's the A.
Yeah. So this is just this evaluated on the surface IV A over 2 pi S squared L. So this is the S vector, and this is the area. All right. So what does that give you? Yes, so that would give you minus I times B, and minus it becomes plus. So dW by dt would become I B. All right, so that is a simple example of conservation law. Now let's talk about conservation of momentum. Now, first of all, by the way, this law is the work energy theorem of electromagnetic field. What does the work energy theorem say in mechanics? The total work done by all forces equals to the change in energy, the change in kinetic energy, basically. So this is kind of the total work done by all forces. In this case, in this example, the force is the electromotive force driving the charges. So the total work done by all forces must be equals to the change in electromagnetic energy. So for momentum to be conserved, what is the condition? Sum of all external forces has to be 0, and also the sum of all internal forces has to be 0, right? But here, if we consider these 2 point charges, charge Q1 and charge Q2, electrical force here is in the opposite direction. So the net internal force of these two particle system is going to be 0 for the electrical part, right? So if both of them are positive, assuming that both of them are positive. So this pushes that one pushes this one, so the net force is 0. What about the magnetic force? This thing is moving with some velocity, so charge is moving, then there is going to be a magnetic field, and because of that magnetic field, this one experiences a force that points up, and the same thing for this one. This one also creates a magnetic field because the charge is moving, and basically that magnetic field, if you write hand rule, at this point is going to be into, and that magnetic field, if you cross it with the velocity, if you cross the velocity of this with the magnetic field, V down and magnetic field into, so you get a force in that direction, right? But when you add these two magnetic force, is it gonna be 0? Yeah, it's not gonna be there. Does that mean that momentum in electromagnetic field is not conserved? And the answer is no, it is conserved. And the reason why it appears that momentum is not conserved is because we didn't consider here the momentum that's carried by the electromagnetic fields. So before we talk about that, then it's really important to know about forces in electromagnetic field. There is an elegant way of expressing force in general, which involves the electric and magnetic forces, which is put in a tensor equation. So this tensor is known as the Maxwell's tensor. So let's find this Maxwell's tensor, or in general, how can we express magnetic and electrical forces combined for a given charge in a given electric and magnetic field. So let's consider, as usual, a volume charge. And the charges are moving with some velocity and are exposed to external electric and magnetic field. So we are going to derive Maxwell's stress tensor. So consider a volume of charge. Consider a volume of charge with charge density rho. And inside this charge, inside this volume, the charges are moving with some velocity v. With some velocity v, and are exposed to electric and magnetic field. To E and B field. So if I consider a small charge dq, or a small charge dq, and want to know the force on this charge, what's going to be? That force, dF, is going to be dq